Okay, and welcome to the second of these videos on the structure and reactions of benzene. This is video number 2. We're going to look at the reactions of arenes. Okay, well, obviously, the interesting thing from the story of benzene structure was that they don't undergo addition reactions. The arenes just don't do that. And there obviously is a reason for this. Benzene, the structure itself, remember, there are 6 delocalized electrons, one from each carbon, which occupy the delocalized electron clouds above and below the plane of the carbon and hydrogen atoms in the benzene ring. The presence of this delocalized ring is very stabilizing, and it keeps the benzene structure together, which means that only the hydrogen atoms that project out from the benzene hexagon are going to be available for any other reagents to attract or react with. So swapping or substituting ring hydrogens for other groups is the type of substitution reaction that arenes will undergo. The benzene ring itself is very, very stable and doesn't get broken or broken up permanently. So we need to look at the electrophilic substitution reactions of benzene, where one of these ring hydrogens is substituted for an electrophile. Now, in order to be able to attack the benzene ring with its delocalized electron cloud, we need electrophiles. These are reagents which are usually positively charged or electron deficient, and they will attract delocalized electrons towards themselves. As you'll see in the mechanisms that follow, there are 4 reactions which are very important at A level. The nitration reaction, the halogenation reactions, that's with chlorine or bromine, and the 2 named reactions referred to as Friedel-Crafts acylation and Friedel-Crafts alkylation. More about those later. The first reaction, the nitration, is very important and is frequently asked. The idea of nitrating, that is putting NO2 groups onto a benzene ring, is very handy in the production of dyestuffs and explosives. So nitration is very important industrially. The way we do these reactions is we use a nitrating mixture. This is a mixture of concentrated nitric acid and concentrated sulfuric acid. The 2 concentrated acids react together to produce an electrophile. So let's just look at that first. The reaction between the 2 acids must be restricted in terms of temperature to less than about 55 or 60 degrees. This is to prevent further multiple nitrations occurring, which could be potentially very dangerous. So first of all, the 2 acids react together to produce an unstable product, the H2NO3 1+ ion. This further now decomposes to produce the all-important nitronium ion. The NO2 1+ ion is the electrophile that we need to generate. So for your purposes, the overall equation in the yellow box is something that you really must remember. So this is how the electrophile is generated. So this is the first part in explaining the reaction. You must know how the electrophile is generated, and the yellow box is the equation you need. Now, the actual mechanism itself is usually worth 3 marks, and it begins with the benzene or whichever substituted arene you already have, and the nitronium ion. Notice the positive charge on the nitrogen. The nitronium ion is therefore very attractive to electrons, and it will pull electrons towards it from the delocalized cloud. As you can see, the arrow moves from where the electrons are, the delocalized ring, towards the electrophile. It must be that way round. The second and subsequent stages involve what we call an intermediate. This is the diagram in the middle. As you can see, the ring itself has been broken open, disrupted. Loss of electrons from the ring means we put a positive charge in the center of it. Now, importantly, you can see the NO2 group is bonding, as well as a ring hydrogen on the same carbon is about to come off. So we recover electrons from the CH bond back into the ring. This will remove the positive charge and it will reform the delocalized electron cloud. So this arrow must come from the middle of that CH bond back into reforming the ring. The product, nitrobenzene, as you can see, is formed, and of course a H plus ion, which came from the ring. Now the role of that H plus ion is to combine with the remnants of the sulfuric acid. This was the HSO4 minus ion from the electrophile formation to regenerate the sulfuric acid. This is often required knowledge as well by combining the H plus with the HSO4 minus to reform the sulfuric acid, shows that it is being regenerated and therefore has acted catalytically. Well, of course, the reaction for nitration is very crucial, very important, worth lots of marks. It's important you know it well. The halogenation reactions require use of either chlorine or bromine to substitute on the benzene ring. Now, in this case, the chlorine or bromine cannot be polarized or turned into an electrophile by benzene itself. It doesn't have sufficient electron density to do that. Instead, we employ a special kind of halogen carrier catalyst. For chlorination, this is aluminium chloride, and for bromination, FeBr3. Both catalysts do exactly the same job. They generate the electrophile. So again, the first step of our reaction, formation of the electrophile, is very important. As you can see from the reactions down to the left here, chlorine with aluminium chloride forms a Cl plus ion and AlCl4 minus. This is due to a dative bond forming between the nearest chlorine and the aluminium. The further away chlorine loses electron and becomes Cl plus, the electrophile. Bromination, exactly the same thing happens. The bromine molecule is polarized by the halogen carrier catalyst to form a Br plus electrophile, and the FeBr4 minus will return later in the reaction. The halogen carrier, again, as you can see, receives electrons from the halogen, leaving the halogen furthest away with a positive charge, thus forming the electrophile. Again, if we look at the chlorination mechanism, same idea, the Cl plus and the benzene ring. The chlorine electrophile Cl plus attracts electrons from the delocalized cloud towards it. Again, the intermediate picture shows the horseshoe intermediate ring with a positive charge. The gap in the horseshoe is directed at the site of substitution, as you can see, and the chlorine that's coming on and the H which is going to be substituted as shown. Well, of course, as before, recovery of the bond electrons from the ring carbon hydrogen bond reforms the delocalized cloud, removing the positive charge and effectively losing that ring hydrogen as a H plus ion. The product is chlorobenzene, and of course keep your eye on that H plus because it reacts with the remnants of the catalyst, the AlCl4 minus ion, to form HCl and to regenerate the aluminium chloride halogen carrier catalyst again. Well, bromination follows exactly the same plan, and of course we'll run through this a bit quicker. The bromine electrophile is attacked by electrons coming from the delocalized cloud towards it, forming a bond to the ring, which disrupts the ring, as you can see, giving the intermediate picture with the positive charge and the broken open delocalized ring structure. Recovery again of the electrons from the CH bond allows reformation of the benzene ring. The H plus ion that was substituted, remember, reacts with the remnants of the iron bromide catalyst to reform FeBr3 so it can do the process all again. And that illustrates the catalytic nature again of the iron bromide in this one. So the two halogenation reactions are very important and the mechanisms are needed. We move on to the two Friedel-Crafts reactions. Now, Friedel-Crafts are two chemists who came up with the idea of being able to actually substitute a carbon group onto a benzene ring. You'd imagine this would be really rather difficult since the benzene ring is not polarized, and of course neither is a carbon naturally. So what they came up with the idea was to use a halogen carrier-like catalyst, aluminium chloride, and use it to create electrophilic carbon plus groups out of haloalkanes or out of acyl halides. Now, in the example here, as you can see, we are trying to substitute carbons onto benzene ring. So this is an example of carbon-carbon bond formation, and it's very important. So what we need to do is create a very positive carbon atom which can attack and attract electrons from the benzene ring. The aluminium chloride halogen carrier catalyst does this. It forms a strong dative bond towards a halogen atom, as in chloroalkane or in the acyl chloride group, and this allows the formation of a positively charged carbon atom. Acyl chlorides or haloalkanes can both be used in Friedel-Crafts reactions. We're going to look at the acylation reaction first. This time we use an acyl chloride. There you go, RCOCl, very polarized, very reactive. The aluminium chloride catalyst essentially removes the chlorine atom from the acyl chloride, leaving behind a positive charge. This carbocation is now able to attack the benzene ring electrophilically. And obviously we can show you the mechanism, although for your syllabus it's not actually required. So as you can see, the basic idea is what you'd expect: attack from the electrophile, the movement of electrons from the benzene ring, the reformation of the benzene ring in the intermediate picture, and as you can see, the catalyst, aluminium chloride, is regenerated by the H from the ring, H plus ion, reacting with the AlCl4 minus to give HCl and the returned catalyst. The alkylation reaction is very, very similar. Instead of an acyl chloride, we use a haloalkane, a chloroalkane. So something like chloromethane or chloroethane or chloropropane, wherever you want the substitution to occur, this is because the chlorine will be effectively replaced by the benzene ring carbon. So again, you can see the aluminium chloride catalyst forming the positive electrophile on the carbon plus. The electrophile can now attack the benzene ring with our now familiar mechanism, as you've seen previously. The idea, of course, is very important because the product has produced a carbon-carbon bond between a benzene ring and an alkyl group. So this is a way of growing a carbon chain on a benzene ring, very important in reaction synthesis.